There's two types of energy transformations to consider. My potential energy is increasing. That's going to require energy. But the other is this. I'm walking, and we know walking at a constant speed on level ground takes energy. So if I compute how much energy it took to climb that hill, I've got to consider both components. But we have to treat them very differently. And that's something we'll consider in the next problem. Let's take a look at a problem. A 68-kilogram hiker climbs to the top of a 200-meter hill. The hike takes 30 minutes of walking at a brisk 5 kilometers per hour clip. How much metabolic energy is required to complete the climb? Let's extract the information that we need to be able to solve the problem. The hiker has a mass of 68 kilograms, and that's going to be used in a couple of different places. The hiker climbs to the top of a 200-meter hill. That's talking about the vertical distance. Horizontally, it's much bigger than that, of course. The hike takes 30 minutes, and the hiker is moving at a brisk 5 kilometers per hour clip. Question, how much metabolic energy is required to complete the climb? Well, let's take a look at this. We've got two different elements to the situation. If we look at a side view of the motion, it looks like this. We have a hill that the hiker is moving up, and the hiker is moving at a particular speed along the slope, and the hiker is going up the hill. So there's two components to the energy use that we need to consider. First off, let's consider the motion along the slope. For a 68-kilogram individual moving at a constant speed of 5 kilometers per hour, the energy use, the power, is 380 watts. So just walking along the slope takes 380 watts, or 380 joules per second. And that will be true on a horizontal surface, or it's also true walking up a slope. That's how much energy is just to move forward. But there's another piece of the puzzle. The hill has a height of 200 meters. The person that's hiking has to increase the potential energy by going up this slope. And that's the second piece of the puzzle. The whole hike takes 30 minutes, and let's take a look at the energy for these two different pieces. First off, the energy for walking at 5 kilometers per hour, and second, the energy necessary to raise the person's mass by 200 meters. We'll do the motion along the slope first. So we're just talking about walking at 5 kilometers per hour. And it turns out it doesn't matter if you're walking up a hill or if you're walking on level ground. If you're walking at 5 kilometers per hour, you're using energy at the rate of 380 joules per second. The walk takes 30 minutes. There are 60 seconds in every minute. There are 30 minutes in 1 hour. And so if we calculate the total energy use for just the walking, just moving forward at 5 kilometers per hour, we get 680 kilojoules. That's the energy required for the horizontal motion. Now notice, we didn't use the 25% efficiency for the body any place in here. And the reason we didn't is this. The value that we have here, the 380 joules per second, that's metabolic energy. That was measured using a spirometer, which measures how much energy the body is using. So this is really honest to goodness how much energy the body uses. So the efficiency is already included in this calculation, and we use that number straight from the table. It's a different story for the second part of the calculation. For the vertical motion, the hiker changes height by 200 meters. There's a 200-meter increase in height. Well, that implies a change in potential energy. And the change in potential energy is equal to the mass, 68 kilograms, times g, 9.8 meters per second squared, times the height, which is 200 meters. And if we work that out, the change in potential energy that we get is 130 kilojoules. But the question asks, how much energy is used to complete the climb? Well, this 130 kilojoules is the change in potential energy. But this change is being affected by burning calories, by using energy from the body's chemical energy storehouse. And so in order to calculate how much energy is used, we have to incorporate the efficiency of the body. To have that much energy output requires 4 times as much energy input. There's 4 times as much energy required by the body in order to do this. So we need to multiply by 4 to take into account the body's efficiency. If we do that, we end up the amount of energy which the body actually uses to complete this, 520 kilojoules. The total energy used to complete this climb is the sum of the two. 680 kilojoules required to walk at 5 kilometers per second, plus the 520 kilojoules required to change the potential energy. So this was, the 680 was the walking, the 520 is the climbing. The total energy is the sum of those two, 1,200 kilojoules. Thinking about this in terms of calories, that's approximately equal to 300 calories, 300 big C calories. So that'll help convert that to food energy. But the interesting thing to note is this. Walking on level ground, 680 kilojoules. Doing the climb, 520. So the fact that you're walking on a hill, in this case, increased the energy expenditure by almost a factor of 2. Not quite, but almost a factor of 2. And how does that make sense in the real world? Let's take a look. We know that walking up a hill is harder than walking on level ground, and it's not a surprise, because to the energy to walk along the level ground, you've added the energy to increase your potential energy. In this problem, we were looking at someone walking up an 8-degree slope. That's a pretty steep slope, and so that is going to take more energy than walking on level ground. Almost twice as much. So it's a significant increase, but it's not 10 times as much. It's not 20 times as much. And so the increase seems reasonable based on our experience of the world, which is good because physics is about the world around us.